Our first speaker is Gerbrand Ceder from University of Berkeley, California. And yeah, I think I'll stop with this one. Everyone who wants to know more about Gerbrand, welcome to Google during this session. Okay, so, please.
How about you Google after the session, okay? It was an enjoyable morning, and I was telling my client that these old papers that he showed, I actually read a few of them as a graduate student, so which makes me feel really old because they weren't old then. Since then, I did my PhD in rather fundamental theory, but since then have moved on to more applied work. But I think Mike's presentation reminded me that there's nothing like a bit of fundamental understanding even when you do applied work. So I'll try to show you that today, that even though I work on batteries, that we have been tremendously helped by fundamental insights that we gained over time in these materials. But I want to set the stage a bit, is that I think what you've seen already, that the world is going electric. This is data from BP's Energy Outlook. They make a report every year or 2 years. This is the 2018. Where they state clearly that by 2040, 70% of all primary energy growth will be in electricity generation. So primary energy is all the energy we use, not just electricity, but also heating, industrial. And so 40% of all that primary energy growth will be satisfied with renewables. And they also predicted that by 2040, 30% of all miles driven will be electric. That doesn't mean 30% of all cars is electric, it means 30% of all miles driven electric, and that was heavily relying on what they thought would be autonomous vehicles, and so we'll see if that becomes true. And of course, if you work with electrical energy, you need large amounts of storage, and storage has sort of penetrated everything from, where many of you probably first met it, which is in your portable phone or laptop. It made a rapid transition to power tools. Today, what's remarkable is that if you're a tinkerer like me, portable power tools now are more powerful than the ones you plug in the wall. This is how good batteries have become. Electric vehicles, and now we see the beginnings of electric flight, and of course, energy storage has been introduced in the grid. And I've put the scale on here, and what you need to realize, going from your cell phone to a car is about 3 orders of magnitude increase in energy storage, and going to the grid is another 3 orders of magnitude. So we're talking about an enormous scaling of the magnitude of the type of energy storage we use, but remarkably, it is today all served by lithium-ion. And there have been many wannabe technologies in energy storage, but if you look at what industry does today, it is almost all lithium-ion. And it's remarkable to see a technology that went all the way with minor modifications from cell phones to what goes in the grid. You can look at a cell that goes in the grid, and 80% of it looks the same than a cell that went into your phone or your laptop. And here's why this is. In 2011, the cost of, this is actually after this conference was started. It was 2007 or so, I believe, right? So during the period of the IWAM conferences, lithium-ion went from over $1,000 per kilowatt hour of storage to today about a bit over $100, and this is at the pack cost. This is when you assemble cells into a pack. But at the cell level, we have reached $100 per kilowatt hour. Now, if you're not into the battery field and you wonder, well, what does that mean? $100 per kilowatt hour is roughly where pumped hydro sits. If you take the energy storage, the average cost of building energy storage by pumping hydro up and down reservoirs, you're roughly at about $100, but with a high variability. So it's remarkable that a chemical technology that was thought of as expensive has essentially reached, pumping lithium ions today is basically as easy as pumping water up and down a hill. So the question is whether lithium-ion will be the victim of its own success and whether the party can continue, and a lot of that has to do with the unanticipated growth. So a lot of the price problems in the market today for lithium-ion are due to the unanticipated growth, and there are all kinds of projections of where lithium-ion will be in 2030. This is one from Benchmark Minerals, predicts 2 terawatt-hour. SNE Research in Korea predicts that we will need 3.4 terawatt-hour. And of course, if you're Elon Musk, you don't want to be left standing in the dust behind. He thinks we should have 20 terawatt-hour by 2030. To put that in perspective, right, if you're not familiar with these numbers, even 1 terawatt-hour will only serve about 10 million EVs per year. That's about 10% of annual light vehicle production in the world. So even if you're sort of only a mild supporter of EVs, you will need multiple terawatt-hour of battery production. And of course, another perspective is with 1 terawatt-hour, you would store China's electricity production for about just 1 hour. Okay. So you may think a terawatt-hour is a big number, but it really isn't. Or something totally useless, you could make 100 billion iPhones with a terawatt-hour. So that requires enormous mineral resources. I'll come into the physics later and show you why we need so much transition metals, typically nickel and cobalt. But typically, for a terawatt-hour, you need roughly 1 million ton of metal. And that math is very simple. You store 1 electron on transition metal. You roughly do it about 3 to 4 volts, so you can all imagine that you can do the math. So remember, a kilowatt-hour is a kilogram of metal, roughly. A terawatt is 1 million tons of metal. So how much do we make? Cobalt production is about a bit over 200 kiloton today, but is expected to peak at about 300 kiloton. Comes out of countries that we don't think of as the most stable or friendly. And obviously, this is not going to make you a terawatt-hour of production. So in the industry, we have substituted cobalt largely by nickel and basically moved from one problem to another. Nickel production is about 2.4 million ton, but most of that, of course, goes to stainless steel production, right? And so we sit sort of here about where maybe we're off-taking about 500,000 ton into the battery industry. And the problem is that batteries need very high-grade nickel. They need what's called class 1 nickel. Almost all nickel produced in the world is lower grade nickel, because it's nickel mixed with iron, because that way you can just throw it in stainless steel together and you never have to upgrade it. Upgrading nickel to class 1 nickel is one of the dirty secrets of the battery industry. Is extremely energy and CO2 intensive, which is why we don't want to do it. So basically we have a problem, and I'll come to the physics of where this problem comes from in a second. If you talk to the Department of Energy in the US or in the UK to the Faraday, they will bring up the magic word whenever you say a resource. The magic word is recycling. We're going to recycle our way out of this problem. Let me show you that that's not going to happen. Okay, so roughly we'll need about, if we believe that EVs are going to take off, and let's say we assume something like 60 million vehicle penetration, that's still only about 60% of all light-duty vehicles produced every year. We'll sort of need about 7 million tons of transition metal. And by the way, if you think this is not real, we are already committed up to here with factories that are going to be built, right? This is not a crazy projection. The world has committed up to 4 terawatt-hour or factories to be built. Okay, so what will recycling do for you? So the problem with recycling is that lithium-ion batteries are too good and too valuable at their end of life. So the warranty on a vehicle is typically that in 10 years, you still need 80% of capacity. So you tell me, when an EV is taken off the market, there is a battery in there that has 80% of capacity, and that battery costs about $15,000. So the question is, will you shred it and barely break even, or will you give it second life? And you know, I'm one of the people in the camp that this is crazy. You are never going to recycle that. You are going to use that for second life, and what that means is that, oops, hate the pointer, that the lag on recycling, meaning the lag from between when the battery was put in production to when it comes back into the metal stream, could be as much as 15 to 20 years. What that means is that if you look at, oh darn, the demand curve, and then when recycling comes back and helps you out, there's this enormous gap. There's a cumulative deficit of about 55 million tons of metal by 2040. This is an enormous number, right? 55 million tons. There are only a few metals in the world that we make at production volumes that will reach that. There are things like iron, manganese, copper, chromium, but that's about it, right? Aluminum, of course, right? But aluminum is not useful to us. Okay, so I want to explain to you the physics of where this problem comes from, and then and show you how sort of fundamental science can actually solve that issue. Many of you are familiar, you saw Raphael's talk yesterday of how a lithium-ion battery operates, and essentially they are intercalation systems. This is still the favorite system of choice, where you, in the cathode, intercalate lithium in a layered oxide typically, and there's sort of this belief that these layered oxides are really good because lithium can sort of diffuse easily into these layers. I'll show you that that's actually a bit of mythology that may not always be correct. And then on the anode side, you tend to use graphite or these days also some amounts of silicon. So this layered class dominates 80% of the lithium-ion industry. Lithium cobalt oxide is what's actually in your cell phone and laptop because the very high density of lithium cobalt oxide. But as we go to higher applications, the cobalt is being substituted by nickel and manganese, and typically by more nickel. And you know, battery people will throw words around like NMC 111, and all that means is that you have equal ratios of nickel, manganese, and cobalt instead of pure cobalt. NMC 811, the current favorite in the industry, means 80% nickel, 10% manganese, 10% cobalt. So basically, we've gone from using pure cobalt to using mostly nickel, and essentially have turned one problem into another. Okay, so I want to go to why only nickel and cobalt. Why can't we make layered oxides with other transition metals? And this was a beautiful piece of work by two of my former graduate students now a long time ago, Anton van der Ven and Kisuk Kang. Anton is a professor at Santa Barbara now, Kisuk Kang is a professor at Seoul National. And they both worked on understanding diffusion of lithium in layered oxides. And here's what actually happens. So here's a sort of cartoon of a layered oxide. When you pull lithium out, this is the skill of my animation level. There's a lot of vacancies there, and transition metals tend to migrate into those vacancies. And they need a single hop, right? Only a single hop. You're going to operate these batteries for 10 years, and you have to prevent a single hop. Because what happens when the transition metal migrates, the layers around it contract. And I'm going to show you that when the layers contract, lithium diffusivity gets completely killed. And so the only metals, as I'll show you, that don't do this is nickel and cobalt. Okay, so why is the lithium diffusion messed up? Because in batteries, we actually like close-packed oxide. Density is a very important thing in batteries. And so almost all the relevant oxides are FCC close-packed. They have ABC stacking of oxygen. And if you look at the topology in there, lithium sits in octahedral sites, and so do the metals. But in FCC, it turns out if you want to diffuse from one octahedron to another, you always have to go to a tetrahedron. Octahedral phase share with tetrahedral phase share with octahedral. And so here's an example of a lithium going from one octahedral site to another. It goes through this tetrahedral site, and there it phase shares with a transition metal in a layered oxide. And when you look a little closer at that configuration, this is actually the activation barrier for diffusion. You are in close contact with a high valent transition metal, so you have a lot of electrostatic repulsion, and that's what sets your activation energy. So now you can see that if you reduce the spacing of these layers, the activation energy shoots up. And that's indeed what ab initio theory confirmed. This is actually the activation barrier as a function of this distance. And what you see even with minor variation, let's say you go from like 2.7 to 2.6, your activation energy shoots up by 100 millielectron volt. That may not seem a lot, but an Arrhenius factor of 56 at room temperature is a factor of 10. So by changing this distance by 0.1 angstrom, your diffusivity has gotten 2 orders of magnitude slower at room temperature, which means that our rate capability is slower. So the sequence of events here is disorder reduces the spacing, and that kills lithium diffusivity, and your game is over. Okay, so now my only piece of electronic structure theory, why only nickel and cobalt? Well, it turns out you have to prevent these elements from diffusion, and they sit in an octahedral site. So what you really want is an element that has very strong ligand preference for octahedral sites and hate tetrahedral sites, which is the intermediate site. So you do a bit of electronic structure theory, right? You look at ligand field splitting of the d orbitals, and roughly here's a cartoon. The 5 d orbitals are split 3 down and 2 up, right? These are the ones with T2G symmetry. These are the ones with EG symmetry. So to be stable in octahedral environment, you need to fill the lower ones and not the upper ones, essentially. And so now you look at sort of the relevant oxidation states of the 3D metals, the sort of relevant ones. So the early ones are completely out because they don't have enough electrons. Like titanium is terrible. We know titanium moves easily all over the place. So these are completely out in battery operation. If you look at chromium, chromium-3 is highly stable with 3 spin polarized electron, but as soon as you oxidize it, you actually lose an electron and it's not stable enough anymore. It starts to migrate. The other thing is chromium disproportionates to chromium-6, and that's highly mobile. Okay, iron is terrible. Iron 3 plus 5 electrons is basically a spherical ion, wants to go all over the place, and so you can't use that one either. And then manganese is bad, if I can use the pointer. There we go. Because manganese 2 also spherical ion, same electron configuration as iron 3, and manganese 3 tends to disproportionate to 2 and 4, so you can't use that either. So here's the periodic table that we have left of the 3D metals. It's basically nickel, manganese, cobalt, NMC. This is why batteries are NMC. The best ion by far, and this was Goodenov's brilliant discovery, is cobalt 3 plus, 6 electrons in low spin configuration. So you have this massive octahedral ligand field stabilization. Cobalt is an ion that on the time span of 100 years does not even make a single hop when you do the calculation. So it's a brilliant material, lithium cobalt oxide. Cobalt never goes anywhere, even when you fully dilithiate that material. Okay, but what this tells you is that people have to stop messing around trying to make layered materials with other transition metals because this is fundamental physics, right? You cannot change the electron configuration, and therefore we are never going to make functioning layered oxides with anything but nickel and manganese as electrochemical elements, and people should stop trying. So the other strategy, which it took us a while to give in, and the other strategy was, well, you could just learn to work with cation disorder. You could accept that the ions move all over the place and see if you can still do decent diffusion, and that led to what's now called a class of disordered rock salts. So the class of disordered rock salts are essentially a close-packed oxide like layered materials, so they are crystalline, but the cations are just disordered over the octahedral sites. And what happens if you have disorder? Now you essentially have statistically all kinds of environments that are around the activated state. So in a layered material, you only have this one, and this one. But now we randomly distribute the ions, so we also, for example, have this environment, only lithiums. And if you look carefully, remember I told you the electrostatics is the problem for lithium diffusion. Here, the electrostatics will be much better because when lithium goes through the tetrahedral site, say this is a vacant site, and typically we have divacancies, it will only see another lithium. So at this point, you have a 1 plus, seeing a 1 plus, you become much more tolerant to contraction of the tetrahedron. And that's indeed, again, what ab initio theory shows, is that if you actually calculate the activation energy in what this is called a 0TM channel, a zero transition metal channel, it doesn't change much as you change the tetrahedron size, whereas if you put one transition metal there, you got a rapid rise. So this was the insight that we could do diffusion in contracted, compacted structures if we could use this environment to diffuse. And this is where my tiny little bit of physics that I learned in graduate school when I was a graduate student and also occasionally took a course in physics, I had learned about percolation theory. And so I realized that, well, this is really a percolation problem. You just need enough of these so that you have macroscopic diffusion. And percolation theory gives you an exact answer that if you randomly distribute it, you just need 10% lithium excess, and you actually will have a percolation network that statistically percolates all the way through the crystal structure. And that was proven in 2014 by us and then by Fichtner and Chen in Germany. Here's actually a stem of a material that is fully disordered rock salt, but you can remarkably well cycle lithium in and out. This is cycling almost 1 lithium per formol unit in and out. And I gotta say, this was such a surprise to many, and including to us, that this is one of the things where when the student comes to you, you say, you must be wrong, this cannot be. And I made him redo it, and it was the same answer. Okay, so that's when we did the theory. Raphael and I wrote a review paper on this, and indeed, today, disordered rock salt cathodes have been made with almost all of the transition metals in the periodic table, all the ones you might ever want to use. So in some sense, we have shed our yoke of the nickel and cobalt dependence. Okay, so today there's a class of DRX cathode materials that use inexpensive materials such as manganese and titanium that are simply made by solid state synthesis. They are very boring in diffraction. They're just rock salts, but I'll show you a little bit about the more complex substructure. There's a version of high entropy oxides that I'll show you in a set with very high rate capability. And then at the end, I'll end saying a little bit about the materials with what's called now partial disorder, which are probably in the long term even more promising for application. Okay, there are some additional benefits that we had not anticipated. Disordered rock salt cathodes often have very low volume change. These are remarkable materials, the molybdenum chromium, here's a vanadium one, where you can take essentially out half the cations, you can take 1 lithium per formula unit out, and there is 0 dimensional change. The dimensional change is below 1% in volume, which means in the lattice parameter, it's like 0.3%. So these materials are of interest for solid-state batteries. We can solid-state batteries where you have mechanical contact between all the solids. You really don't want to have any interfaces that move around. Okay. Another benefit that we had not anticipated, but we found later, is that these materials can take up fluorine in the synthesis. And the reason that they can do it is because statistically they have some environments where there's a lot of lithium around the anion, and fluorine particularly likes that, and so fluorine substitutes in there. Again, something is much harder to do in these layered ordered oxides. And we've worked with Raphael to confirm this with NMR, because of course it's quite hard to detect fluorine in your materials by other techniques. Fluorine does great things for you. This gets a little more technical, but many cathode materials have gas release when you charge them to high voltage. And what happens with fluorine is that this is actually DEMS data, so this is actually where you charge a cell and measure the gas coming off, have only a very small amount of oxygen coming off, even at high voltage, much less than a classic material. The reason that gas coming off is important, it tends to swell the cell, but also oxygen gas is particularly bad because it's essentially an oxidant and you have an organic solvent that you can combust with it. So extremely small amount of oxygen coming off, and that's because fluorine passivates the surface. This is some data from Changmin Wang at Pacific Northwest National Lab. If you take a disordered rock salt without fluorine and then you compare it to a similar one with fluorine, these are cycled 50 times to very high potential. It's a little hard to see, but this has undergone all kinds of corrosion holes, essentially where materials have dissolved, and the fluorine-containing material is perfectly intact. And essentially, it's because what Raphael said yesterday, fluorine is an extremely electronegative ion. It's almost impossible to oxidize it unless you go to really high potential. Okay, so these materials look boring structurally at first in X-ray diffraction. But what we found, and others have found, is that there's really a subtle structural complexity which turns out to be remarkably important for performance, and it has to do with short-range cation order. So remember that for transport, you really want to build a lot of these, what are called now 0TM channels, right? These tetrahedral configurations of lithium, they're the key to lithium transport. But if you think a bit about, this is probably not a preferred environment because you sort of have 4 1+ cations. So what actually happens even when they are statistically disordered is that you tend to build short-range order where the transition metal wants to be nearest neighbor to the lithium. And the short-range cation order is actually destructive to transport because it destroys these 0TM channels. And you actually see that when you do electron diffraction. So you see the typical Bragg peaks, and then you see this diffuse scattering, which is very pronounced, which is an indication of short-range order. And I'll show you is extremely destructive to the performance. So here's an example that didn't turn out the way we did it. And if I can give my message to young people, an experiment doesn't always come out the way you want it, and sometimes it's completely the wrong way, and usually that's a great learning moment that you can actually learn something. So we made 2 oxides that we thought would be similar, but we thought this one would be better. So this is a 20% lithium excess with manganese, and then there's zirconium as an inactive element, and then we replaced that here by titanium. We thought this would be the better material because zirconium is bigger. And we thought zirconium is bigger, so you have better diffusion of the lithium. Well, when we did the experiment, this is cycling data, and you don't have to know much about this except this is capacity. So you can see that the zirconium was much worse than the titanium. These were materials synthesized under exactly the same conditions, cells made under the same conditions. And what you see is that the zirconium one has very pronounced short-range order, to the point where actually this diffuse scattering is starting to sharpen up, and meaning the extent of the short-range order is becoming pretty long, whereas in the manganese one, it's actually, in the titanium one, it's actually a little less diffuse. So materials that are almost the same, again, except differ in their short-range order, and if you look at ab initio simulations, this is the percolation network in the titanium one, and this is the percolation network in the zirconium one. As you see, this is much more pronounced. Here, disorder has destroyed almost completely your percolation network. So this is something we had to learn to deal with, because short-range order is not that easy to quantify, and especially not in diffraction techniques. We came up with ways to kill the short-range order, reduce it, and one way was from talking to some of my colleagues, which is also occasionally useful to talk to your colleagues. I had some metallurgy colleagues who had just been working on high-entropy alloys to remove short-range order for improving ductility of materials. That was actually Rob Ritchie and a bunch of people. I know his name was mentioned before. So we thought we can do the same in cathode materials, and here's sort of a bit of an experiment. So we made cathode disordered rock salt with successively more metals in them to sort of do a high entropy effect. So I'm first starting with, they all will have 30% lithium excess, they have the same anion configuration, and then I'm going to put more and more metals in. So I first start with 0.4 manganese and 0.3 titanium. You know, that gives you a lot of short range order, as you can see, and it gives you sort of respectable performance. Okay. So now I'm actually increasing, I'm splitting the manganese 3 into manganese 2 and manganese 3, and I'm splitting the titanium and niobium. So I have essentially, for a configuration entropy perspective, 4 metals, even though I have only 3 chemistries, but these are different valence state. You see that the short range order weakens and the performance gets better. This is all tested under the same conditions. Now I go to 6 elements. I split the manganese 2 in manganese and chromium, cobalt. I split the manganese 3 in chromium and manganese, and these are split. So I have 6 elements. I have no sign whatever of short-range order. It's completely random alloy now, and now I have by far the best performance. I have 955 watt-hours per kg. So simply by destroying the short-range order by a high entropy effect. These materials also have extremely good rate performance. This is more of a side issue. But rate performance, which is the ability to charge and discharge fast, depends on the diffusivity. And here we can discharge at 2,000 milliamps per gram, which is something like do a full charge or discharge in 5 to 6 minutes, which is remarkable for a battery material. Okay. You can also do controlled annealing. We found by doing in situ electron diffraction that when you actually make this material, remarkably, it first makes the fully disordered rock salt, and only over time does it start to introduce short-range order. So what we actually found is that if we do only very short synthesis times of these materials, we can actually also reduce the short-range order. See, this is 5 minutes. You already have the Bragg peaks of the rock salt, but when you go to 4 hours, you start getting a lot of this sort of short-range order streaking. And indeed, the materials that have short annealing times, even with the same particle size, always have higher capacity because they have better rate performance. Okay. So this is an example of where we went from basic science. This is now a large program of the Department of Energy. The Department of Energy just set up a big, what's called the DRX Plus consortium, which is a $5 million a year consortium for 3 years to solve the remaining problems to scale up these materials and bring them to industry. And if this works, the outcome will be important, right? Because we can work with titanium and manganese precursors instead of nickel and cobalt. These cost about $1 a kilogram compared to about $25 to $50 for nickel and cobalt. So this could bring lithium ion down to something like $50 to $75 a kilowatt hour, which at that point it is really hard to beat for any other technology. So we'll see if we get there. But I want to end with a few slides sort of looking forward, because I think this opened up our eyes that there was a whole space of new materials out there that maybe was somewhat unconventional. For 20 years, the lithium-ion field, including myself, looked heavily into what I would call conventional cathodes. These were well-ordered materials, And if anything, we were trying to completely get rid of any disorder. And then we did fully disordered materials. So these are crystalline but cation disordered. That's the DRX class. And now we've been looking, I think if we work in the middle, where we have sort of materials that are still long-range ordered, but with very high degrees of disorder, we can probably do even better. And I'm going to show you an example of that. The example is a classic spinel, a material that's familiar to many of you. And Mike Thackeray, when he was working with John Goodenough in Oxford, kind of came up with this spinel as a battery material. This is the composition here, LiMn2O4, and this in industry was used by lithium extraction, so only this part. This is where you reduce the lithium content to Mn2O4. This actually was used as a commercial product for a while. It went into the Nissan Leaf, but it's been superseded by the NMCs because the capacity is too small. But there's actually a whole lot of extra capacity sitting here, which you can reach by inserting lithium from LiMn2O4 to Li2Mn2O4. The reason this is not used in industry is because this is a first-order transition. This is actually a two-phase reaction, which is why the voltage is flat. And a two-phase reaction, by definition, is inhomogeneous in the way it occurs. So that means it causes stress and strain in the material, and it fractures the particles in situ. So again, back to physics courses, I had sort of learned that with disorder, you could reduce first-order transitions to second-order transitions, and in some cases even remove them. And that's what we try to do. Could we introduce spinel disorder between the 16D and 16C sites? These are nominally empty in a spinel, and these are filled, to actually kill this first-order transition and make it second-order or make it disappear at all. And we did some theory. This is some ab initio simulations where we simulate the voltage profile, and this is what we're looking at. And we're systematically introducing disorder and see how the equilibrium lithiation increases. So first we make a very small amount of disorder on the 16C sites. We make more. What you see is this plateau is starting to shorten. You make even more. This plateau shortens more. And by the time you hit about 25% of disorder, so it's a very substantial amount of disorder, the two-phase region is completely gone. And you now have a material that can completely operate through solid solution and would be a much better cathode material. So the question is, can you make this material? Okay. Well, it turns out you can by heavy ball milling. If you do heavy ball milling, you can make these unusual spinels, which are neither stoichiometric nor fully ordered. So this is a spinel that's only partially occupied on the 8A side, has almost full occupancy on 16D, the normally occupied spinel, but also has occupancy on 16D. So this was both X-ray and neutron refined. And you can make multiple versions of that. This is versions with different amount of fluorine. And these materials work remarkably well. They are probably today the best performing intercalation cathodes we have ever seen. This material achieves about 1100 watt-hours per kilogram. To put that in contrast, a typical NMC is about 700 or 750. Does it with very good cycling, but maybe remarkable, does it with amazing rate capability. So here's a discharge at 2 amps per gram. Again, typically we look at things that do like 20 or 100 milliamps per gram. So this material not only has amazing energy density, but also has amazing rate capability. And by the way, it only uses manganese, right? One of our cheaper transition metals. But of course, what is the problem with these materials? That we do not know how to make them with scalable synthesis methods, right? Because we use them by heavy ball milling. This is how we can make this large level of disorder. But ball milling is not a way that you're going to make 100,000 kilograms of material. And so this is the challenge now. How do you make these materials with that level of disorder in a more scalable and controlled way? So let me end with that and say that I think there's a whole new space here of cathode materials in the space of disordered and partially disordered materials that you can use earth-abundant materials with, and really I think have a lot of potential for the industry. So let me thank my team here, and I'll be happy to take questions. So thank you.
Thank you very much for your clear and interesting presentation. Do we have questions? Yeah, Tony, please. Let me give you.
Thanks very much, Gerd, for a wonderful presentation. I hadn't realized how much what the stuff that you're now doing relates to my PhD work. like a million years ago. And have you, I can explain the details of that later, but have all your compounds, say the rock salts, are stoichiometric on the metal sides? And have you explored systems where you might be able to enhance the lithium diffusion by having substoichiometric metal occupancy on the octahedral sides?
So most of them are stoichiometric, but we have experimented a little bit with materials that are sub-stoichiometric or even trying to go over stoichiometric, so fill some of the tetrahedral sites. And I clearly should talk to you because we have not been able with regular solid state methods to make sub or super stoichiometric ones, but with ball milling you can, right? So with ball milling you can make sub-stoichiometric oxides, and they have certain benefits that we can talk about offline. You can modify the short-range order actually considerably by going sub-stoichiometric because you're shifting the valence on the transition metal in the synthesized state.
So the classical example where it's sub-stoichiometric on the metal side is FeO.
Yeah,
and
of course. Yeah.
You can't make FeO.
Yeah.
And it's always sort of iron deficient.
Yeah.
But it also has tetrahedral iron interstitials as well. But anyway, we could talk about this offline. I think it's maybe some real scope there.
Great, thank you.
Any other questions? Yes, please.
Hi, thanks. Really beautiful diffuse scattering for the partially disordered rock salts. So from my understanding of what you're saying is that when you start introducing more order into those materials, you're causing problems because you're effectively disfavoring those great zero transition metal sites. Is it possible, I mean, I imagine you've thought about this much more detail. Is it possible to come up with some kind of chemical change that would introduce order in the opposite sense? I know charge neutrality is working quite hard against that, but you could get partials or the other way around, I guess.
So it's a great question because not all short-range order, of course, is made equal, right? There's a sort of high-dimensional space, and there is a type of short-range order that would actually be beneficial, right? And that's actually the one of the spinel type because if you look at in spinels, you make tetrahedra with either only lithium, only metals, or 2 and 2. And so that short-range order is extremely hard to induce. So most short-range order that you form is the one that's electrostatically favored, which you call the lithium iron oxide type. It tends to be the one that you electrostatically favor, and that is always detrimental for your percolation. But yeah, in principle, there is short-range order that would be even better than the random limit. Mm-hmm. So we always set the random limit as sort of our target, but in principle, there's a short-range order domain on the other side. That's even better.
Thanks.
Yeah. One last question. Yes, please.
Very nice talk. I just have a curiosity. The annealing temperature should have certain role on the strength of your short-range order. So is it how the samples are made, the condition and etc. has an influence on the short-range order?
I'm sorry, could you repeat the first part of the question? Was it about
so the question was how the samples were made, the annealing condition of the samples being made, that will have a role on the short-range order.
Yeah, certainly. So the annealing time, certainly, I went very quickly over that. So what we find is that if you track in situ the formation of short-range order or the formation of the rock salt even, the rock salt forms very quickly from the precursors, but it's actually not short-range ordered. Mm-hmm. And then as you sit around, the short-range order tends to form and then stabilize it because it's actually an equilibrium short-range order, right? It's an equilibrium phenomena. So there is a certain opportunity if you quench where you can actually reduce the short-range order. Practically, it's non-trivial to quench on an industrial scale, but there's certainly an opportunity there.
Okay, thanks.
Right, as the chairman, I'll allow myself the last question.
Oh.
Yeah, so the extreme case of disorder would be nanoparticles. Is this a feasible route, or is it cost too prohibitive?
No, it's a great point. So the problem with nanoparticles is that there are two challenges to use nanoparticles in batteries. One is that you create a lot of surface area, of course, in nanoparticles, and cathode materials tend to be reactive with the electrolyte. So if you make more surface area, you have more reactivity, unless you have an absolutely stable cathode. That's one thing. But the other practical problem is what the industry cares most about is energy by volume, not energy by weight. And nanoparticles are really hard to pack densely. So if you make an electrode, nanoparticles, because they have such poor particle-particle contact, it's extremely hard to make an electrode where you highly densify the stuff. So it's more of a practical problem, to be honest.
Okay, thank you very much.